Okay, good day. This is Dual Enrollment Pre-Calculus. I am Mr. McCulley, and this is lesson number 31 on vectors. Let's get right to it. So today we are going to talk about vectors. There's a lot of stuff, a lot of new information for vectors, but none of it is hard. So we've got to balance all of the new stuff with the amount of things that we've got to get through. So let's talk about our goals here. We're going to represent vectors as directed line segments and write them as component vectors. We're going to perform some basic vector operations, add and subtract, scalar multiplication. We're going to write a vector as a combination of unit vectors, and we're going to find the direction angle of a vector. So what is a vector? The component form of a vector is the ordered pair for the endpoint of a vector with an initial point at the origin. And so essentially what we're saying here is that if you have and we'll just do a simple one, just a real simple example right here. If I had the vector, let's say I had 1, 2, all right? Basically what we're saying is for that vector there at 1 on the x-axis and at 2 on the y-axis, we start at the origin, we come up to here, and we show that there is a direction. So we're going from the origin to this point at 1, 2. So real simple. The magnitude of a vector is the same as the distance, and so when you see these double bars with V with a little arrow on it, it's kind of hard to see, so I'm going to draw it a little bit bigger over here by the side and say vectors can be represented in a number of different ways, and you could have a variable with a line over the top with like a half arrow going there, or sometimes they'll do it in the book, and I think in the book they do it this way all the time, almost all the time. They can do it as boldface as well, and so both of these are also ways that we can say vector v. And so you'll see this kind of looks like the Pythagorean theorem, in fact that it is. So if I were to want to know the magnitude of the vector, that's the same as the distance. And so if I come over here and I draw in a right angle, you could say that this side right here is A and this side right here is B, and so the distance, the magnitude is the length of the vector, and since it's a right triangle, we go a squared plus b squared equals c squared, and if I want to just find c, I take the square root of the a squared plus b squared, so that's pretty straightforward. Scalar multiplication, if you have a constant times a vector, all you have to do is multiply each of the two components by that constant value. If you're adding two vectors, you add the x values and then you add the y values, and so a comma b plus c comma d is a plus c, b plus d. We have two standard unit vectors. We have a horizontal unit vector. We call that I, and it's not the imaginary number that we talked about earlier in the section in the class. It is just a unit vector of vector length 1. So if we're in the x-axis, this vector right here is our I vector. And we have on the y-axis, if this is 1, then our j vector is a vertical axis vector. Call that j. All right. To find a unit vector in the same direction, but it has so find a unit vector. It'll have the same direction as a regular vector, but it'll only have a magnitude of 1. And the way that we find the unit vector, that's why they use a u in this particular instance. They use a lot of u's and v's when you're talking about two vectors, is by finding the magnitude of the vector, take the reciprocal of that magnitude, and then use that as a scalar and multiply by the component form of the vector. And we'll talk about that here in a little bit. Some properties that hold true for scalar or for vector addition and scalar multiplication. The commutative property of vector addition holds, the associative property of vector addition holds, the identity property of vector addition holds, the inverse property of vector addition holds, the associative property of scalar multiplication holds, the distributive property of vector multiplication vector and scalar multiplication holds, and the identity property of scalar multiplication holds. All right, let's talk some examples here. And so my first example says show that the two vectors are equivalent. So vectors, vectors, are equivalent if their magnitudes are the same. All right, so I don't want to spend a bunch of time going through this stuff when all I have to do is show that they have the same distance. So I'm going to come over here, and I'm just going to make us a little smaller. I'm going to go, all right, let's see here. If I go 1, 2, 3, that has 3. 1, 2, 3, 4, I think I messed up. 1, 2, 3, 4, 5, 6, 7, 8. That's 8. So the magnitude in this one here is vector u, and I want black again. So magnitude of vector u would be equal to the square root of 3 squared plus 8 squared. And then the magnitude of vector v, well, let's do that again, and let's get the same. So 1, 2, 3, 4, 5, 6, 7, 8, and an 8 there. 1, 2, 3, and a 3 there. So the magnitude of vector v is also 3 squared plus 8 squared. So we could calculate that if we wanted to, but we can just, I mean, you put it in your calculator to simplify a radical. We've done that before. But we can say thus u, vector u, and vector v are equivalent. All right. Next one, find the component form of a vector that has an initial point of negative 2, 7 and a terminal point of 5, 17, negative 17. So just real quick, and again, not real important for us, but we just want to have a general idea. So at negative 2, 7, so if I come over here, I call this negative 2, I call that 7 on my x-axis, or that's my y-axis. Come on, Macaulay, get with it. Let's see here, don't like that there. Okay, 7. There's my initial point, and then I have a terminal point at 5, and then we'll call that negative 17. So we'll call that 5 right there. And so let's put a little ray, initial point, final point right there. That looks good. So to find the component form, subtract the initial point from the terminal point. So the component form of, we'll call this vector v just for the sake of argument. Vector v in component form is going to be, I'm going to go 5 minus negative 2, so 5 minus negative 2, comma, negative 17 minus 7, and so my final answer is going to be 7, comma, negative 24. And so from start to finish, we go 7 to the right and down 24, and that kind of looks like what we have there. So I feel fairly confident in that. All right, given that vector u is 5, 3 and vector v is negative 4, 0, let's find some of these values here. And so this one here says simple vector addition. So I am just adding the x's, so 5 plus negative 4. And then 3 plus 0 is going to 5, and negative 4 is 1. 3 and 0 is 3. Put the vector brackets around it, and we're good. If I want to do a vector subtraction, I do the same basic operation, except we're subtracting now. 5 minus negative 4 is 9. And then 3 minus 0 is still 3. We're good there. Here, we're asking me to do a subtraction again, but this time we have to do a scalar multiplication first. And so a scalar, oops, didn't mean to do that. Scalar multiplication. So I'm going to go 2 times 5 comma 3 minus 3 times negative 4 comma 0. So I've got to do that first. That's going to give me 10, 6 minus negative 12, 0, which will be 10 plus, because minus a negative, plus 12, comma 6 minus 0, leaves me with, let's see here, so 22, the vector, and 6. There we go. And then this one, half. Oh, we're gonna have some fractions, so we'll just get it done. Same thing, we're adding, so it's a half, and then it'll be 5, 3, and then plus 4, negative 4, 0. And so let's see here, I got 5 over 2, comma 3 over 2 when I do the scalar multiple to the first one, and then it'll be plus negative 16, comma 0. And let's see, there will be negative 32 halves. So it'll be 5 halves minus 32 halves, comma 3 halves plus 0. And if I do that subtraction right, I'm thinking it's negative 27 over 2, comma 3 over 2. That looks right. All right. Okay, so next example here, we're going to find a vector with a given magnitude in the same direction as the given vector. So what we're looking for is we're going to find a new vector, and we're going to call it v, and we want that vector's magnitude to be 3. And so but we also want it to be in the same direction as negative 12, 5. So let's see here, real quick, let's draw. And let's do it like this, and we'll go negative 12 here, and 5 there. Draw in that vector. Okay, so clearly this vector right here, this vector that we were given u, is not, it's not 3 units long. In fact, it's a lot longer than that, because even if we pulled it straight up there, that vector is 12, and so this vector has to be longer than 12, and I don't know what it is. So the way that we're going to do that is we are going to, first we're going to find the unit vector, and then we are going to do a scalar multiplication of the magnitude of v, which is 3 in this particular instance. Okay, so if we go back to an earlier slide, we see that finding the unit vector, we're going to find the magnitude of the current vector, go 1 over that current vector, and multiply by its component form. So to find the magnitude of u, we're going to say that the magnitude of, not v, the magnitude of u is going to be equal to the square root of negative 12 quantity squared plus negative 5 quantity squared. And just real quick with calculator, 12 squared plus 5 squared is 169. Square root, second answer, 13. So we're pretty good there. So this is 13. That is the length of that. And so our unit vector, I'm just going to call it the unit vector because I'm already using u and v. I'm going to go 1 over 13 times this value here. So negative 12, comma, negative 5, and that will give me negative 12 over 13, comma, negative 5 over 13. And now this is clearly, this is less than 1 and this is less than 1. And so if I square and add those, I'm going to assume that I'm going to get 1, and I'm fairly certain of that. So I've got a new vector here. We'll just grab this and change it to red real quick. Got a new vector that is 1 unit long, where this one was longer than 12. And so to find vector v, we're going to take this new component unit vector and multiply it by the magnitude of the vector that we're looking for. So 3 times negative 12 over 13, comma, negative 5. Got ahead of myself. Negative 5 over 13. And so when I distribute, I'm going to get, let's see here, negative 36 over 13, and that doesn't reduce, and negative 15 over 13, and that doesn't reduce either. So there is my unit, or my vector v, that is 3 units long, and it's in the same direction as that vector there. All right, let's see here. Find the magnitude and direction angle for the vector v, given that vector v is 8i minus 3j. Now, if you remember from earlier, the I vector is 1, 0, and the j vector is 0, 1. And so what we can do is we can convert this into component form by saying that this thing here is a times 1, 0 minus 3 times 0, 1, and then that will give us 8, negative 3 when we simplify it. Now, we don't have to do this all the time. We can just say, okay, 8 and then negative 3 and go right there. And that'll make it easier. So we want to find the magnitude and direction angle of that vector. All right, so if I were to, and I don't want black, I want black. Let's change it to black. If I were to go 8, negative 3, and just real quick, we'll call that 8, we'll call that negative 3, and we'll put in a vector for that point right there. In the standard position, we're trying to find that angle, and we could find it either as a negative angle, or you could come all the way around and get that fairly simple. But the magnitude is easy. It's going to be the magnitude of v is equal to the square root of 8 squared plus 3 squared. And I know it's negative 3, but it's going to be positive when we square it. So we've got 64, and 9 is going to be the square root of 73, which is a prime number, I think, so I'm going to leave it like that. And then the angle measure, well, if I'm trying to find this theta, and this length is 8, and this length here is negative 3, or we can make it positive 3 and just make that smaller angle there. I know 2 values, so I'm going to go the tangent of theta is equal to, and I think I'm going to go opposite as positive 3 over 8, and then we'll just say it's going to be a negative. We're going to get a positive value. We're just going to say that it's negative because we know that it's opening that way. So theta equals, let's see here, the arctangent of 3 over 8. We'll put that in the calculator, get a decimal answer, but let's check our mode. We are in degree mode. That's awesome. So second arctangent of 3 over 8, close the parentheses, and so negative 22.556 degrees. Negative 20.556. So negative 20.556 degrees. Box that off. We have now found the magnitude and the direction angle. Okay. Next, find the component form of v given its magnitude and the angle it makes with the positive axis. Okay. So what we could do here is we could say that this particular vector, just real simple, is we can say that this is going to be equal to, or the component form is going to be the vector of v, and we're going to multiply that by the horizontal vector I times the cosine of theta plus the j vector times the sine of theta. And for this, it's just a plug and chug. So we can go 5 over 2, and so I is 1, 0, and j is 0, 1. That should be a theta, sorry. We'll leave an I there, and the cosine of 135 degrees plus j times the sine of 135 degrees, and we've all memorized our unit circle and know that the cosine is negative square root of 2 over 2, so I've got 5 times 2. Let's see here, it'll be 2 square root of 2 over 2. Yeah, that's not very good. Square root of 2 over 2, and the cosine's negative in the second quadrant, and the sine is positive in the second quadrant. And so when I distribute, I will finish that off with 5, negative 5 square root of 2 all over 4, comma 5 square root of 2 all over 4. And so that is the component form of a vector that has a length of 5 halves and a angle measure of 135 degrees right there. Well, that's all I have for you today, folks. So our super Star Wars fun fact of the day: the capital world city of Coruscant never actually appeared in the original Star Wars trilogy when it was released back in the late 70s and early 80s. The name was coined by the author Timothy Zahn in his Expanded Universe book, Heir to the Empire. George Lucas liked it so much that he made it canon, and it was the capital planet for the prequel trilogy. That's all I got, folks. Have a good day. See ya. Goodbye.